In this video, we're going to be looking at two KEQ calculations that are a little bit less straightforward than the ones from the previous video. We can start this one by writing our equation for KEQ by simply taking the concentration of our products, sulfur trioxide and nitrogen monoxide, and dividing them by the concentration of our reactants, sulfur dioxide and nitrogen dioxide. In this case, we're actually given the value for KEQ, which is 3.5. However, if we look at the initial quantities that we're given, we have two problems with them. Firstly, that they're both listed in moles instead of being listed in concentration, but that's an easy thing that we can fix. 4 divided by 5 we know is 0.80, which means that the initial concentrations of both of these measurements, our reactants, are both 0.80 moles per liter. Now, the second problem that we're given is that we're told that these initial quantities are placed in a reaction flask and allowed to equilibrate, which means that we're not told any information about the equilibrium quantities. That's what we need to actually calculate here. So because we're given the initial quantities of each of our reactants, we can go ahead and write those into our RICE table like so. Since we're not given any information about the product concentrations, they are assumed to be 0, which means we know the way that our equilibrium is going to shift. Because there are no products, there can't be a reverse reaction, which means our equilibrium is going to shift to the products. And because we know the stoichiometric ratios of all of our reactants and products are 1 to 1 to 1 to 1, that means that our magnitude of change for all reactants and products is going to be X. Because we're shifting to the products, it's going to be positive X for the products and negative X for the reactants, which means that if we calculate X, we have found the concentrations of each of our products, and then we simply need to take our initial quantity of each of the reactants and subtract X from them. The problem with this question comes from actually calculating the value of X, because we actually need to use KEQ, or rather the equation we've set up for KEQ, in order to calculate the value of X. So I'm going to substitute those values in now. We know the concentration of both of our products are X, and X times X is X squared, and we know that the concentration of each of the reactants is going to be the same, 0.80 minus X, and when we take this and multiply by itself, we get A squared as well. Now, we could expand out the denominator using FOIL, or we can use a workaround by taking the square root of both sides, thereby eliminating the exponents on the KEQ side. So that would mean that root of our KEQ constant, 3.5, is equal to X over 0.80 minus X. So in order to solve for X, we need to isolate for X, which means that we're going to take our denominator and multiply it by the root of 3.5. So that's exactly what we're going to do in the next step. And from here, in order to isolate X, we need to expand this outward, which is what we can do in the next step. So root of 3.5 times 0.80 minus root of 3.5x. Now here, you'll notice that I'm not putting this number into a calculator because we don't want to round until the very final step to remove any rounding error that occurs. Next, what we're going to do, I'm going to spare you the details of the algebra here in terms of showing it, but we're going to move the minus root of 3.5x over to the right side so that all of our x terms are on the same side, and then I'm going to divide both sides by the coefficient that we have in order to isolate x, and that's all I'm going to show in the next step. So we're going to assume that x is isolated, and we have root of 3.5 times 0.8 divided by the coefficient that we would have, which is 1 plus root of 3.5, which is the coefficient. And if you put this into your calculator, you'll find that x comes to approximately 0.52 with two significant digits. So based on our rice table, we have just figured out the concentrations of sulfur trioxide and nitrogen monoxide, and all we need to do to find the concentrations of our reactants, that being sulfur dioxide and nitrogen dioxide, is simply take our initial concentration, 0.80 moles per liter, and subtract x. And if you subtract the unrounded value here, you should come up with a concentration of approximately 0.28 moles per liter. In the next question, we actually need to deal with a situation involving Le Chatelier's principle. So in this situation, if we look at the initial quantities that were given, again, we see all of them are in moles, but fortunately our volume is 1 liter, which means if we divide all of these numbers by themselves, the numbers don't change, so we can just go ahead and convert all of these moles into moles per liter, so that we're good. Next, we're going to put all of this information into the initial table of our rice table, because these are the initial concentrations that were given. So 1 mole per liter of sulfur dioxide, and then 4 moles per liter of everything else. Now, for the observant among you that read the rest of the question, we're told that the reaction container contains all of these quantities that are at equilibrium. So if we're at equilibrium, why are we writing these under the initial conditions? Well, that comes when we look at this however statement here. However, 3 more moles of sulfur dioxide are added to the mixture, which means that under our initial conditions that cause the equilibrium shift, these conditions that I've written in are at equilibrium, which means that no shift occurs. However, when we add these 3 more moles per liter of sulfur dioxide, this is a stimulus to the system, which means that based on Le Chatelier's principle, whatever this stimulus does, the equilibrium is going to try and reverse this. And we know because of rates, whenever we introduce more particles of that reactant, we're going to have more collisions. So that means our reactants are going to have more collisions, which means that the equilibrium is going to shift to the products, because if there are more collisions in our reactants, our forward rate is now greater than the reverse rate, causing the equilibrium to shift this way, which means that we know our products are going to change by a factor of positive x, while our reactants are going to change by a factor of negative x, which makes it relatively easy to calculate what the equilibrium concentrations of our products and reactants are going to be. In the case of the products, initial concentration 4.0 moles per liter plus X, and conveniently our reactants are simply 4.0 moles per liter minus X, and because the total initial concentration of sulfur dioxide is the same, it would be the same as well. Now, the problem comes when we actually try and solve this question. If we want to put all of these into our KEQ expression, which is the same as in the previous example that we did, you'll find that something is missing. You'll find that in this example, the question doesn't actually give you the value of KEQ. There is no value of the equilibrium constant that's given. However, you don't need it because we can calculate it, because the initial conditions that we were given here are at equilibrium, which means we can calculate what the value of KEQ is going to be, and we don't even need a calculator to do it. So if we put in 4.0 moles per liter of each of our products, this would be 4 times 4, which we know is 16, but we don't even need to do that because of the reactant concentrations, which are 4 and 1 moles per liter. 4 divided by 4 is 1, so these cancel out, which means that our KEQ value is 4 and no calculator is needed. So even though the question doesn't give us the value of KEQ, we can still calculate it using the initial conditions, and now it comes time to actually solve for what the value of X is. So here, because the concentrations of each of our products and each of our reactants are the same, whenever you take anything and multiply it by itself, we can represent that by simply writing 4.0 plus X squared. And the same goes for our reactants, 4.0 minus X squared. And then we can use that workaround by taking the square root of both sides in order to eliminate the exponents. Square root of 4 is 2. So we have 2 is equal to 4.0 plus X over 4.0 minus X, and then it simply becomes a matter of isolating for X in order to solve. So we're going to multiply both sides by the denominator, so 2 times 4.0 minus X is equal to 4.0 plus X, and then we can simply expand this outward and then move X to the same side and all of our constants to the other side. So let's go ahead and do that. So we have 8.0 minus 2x is equal to 4.0 plus x. So we're going to move all of our x terms to the right and all of our constant terms to the left, which means we would have 4.0 is equal to 3x, which means that if we divide both sides by 3, x is equal to 4.0 divided by 3, and all that we have to do now is put them into our equilibrium concentrations. So let's start with the products. So the concentration of sulfur trioxide and nitrogen monoxide is equal to 4.0 plus 4 over 3. And we don't even need a calculator to do this, because if we simply express 4 as a fraction with 3 as the denominator, we get 12 over 3 plus 4 over 3 comes to 16 over 3 moles per liter. No calculator required. And we can do the same thing with our reactants, sulfur dioxide and nitrogen dioxide, which would be equal to 4.0 minus 4 over 3. So again, we can do the same thing, convert 4 into a fraction with the denominator of 3. 12 over 3 minus 4 over 3 comes to 8 over 3, and we have just figured out the concentration of our reactants. So once again, in both cases, even if the arithmetic and algebra is not particularly complicated, the key with solving complex multi-step equilibrium calculations like this is always to make sure that you have the right KEQ and that you know which stage of the equilibrium shift the measurements correspond to.